Greetings, welcome to 4.23 Nutrition Labels. The nutrition label on a bag of potato chips says that 1 ounce, 28 grams, serving of potato chips has 130 calories. It contains 10 grams of fat with 3 grams of saturated fat. Good reason not to eat too many of these. A random sample of 35 bags yields a sample mean of 134 calories with a standard deviation of 17 calories. Is there evidence that the nutrition label does not provide an accurate measure of calories in the bags of potato chips? We have verified the independent sample size and skew conditions, so we can go forth and do a hypothesis test. In other words, that's what they're giving us a hint here. So in other words, to find out if there's evidence if the label is wrong, we will use a hypothesis test. So what that means is we have to come in first off is we need to go ahead and state our null and our alternate hypotheses. It's always one of the first steps in a hypothesis test is be clear and explicit about what the null and the alternate hypotheses are. So in this case, the population mean calories is equal to 130 calories per bag, would be what the null would say. The alternate says, nope, not thinking that's right. I think it differs from 130. So we're going to do a two-tailed test here, which is equivalent to doing a confidence interval. We'll talk more about that at the end. Okay, once you've set up your hypotheses, the next piece of the computation is to computate your test statistic. So our test stat, in this case, is going to be our old pal z. We're going to calculate that by taking x bar minus mu of the null divided by the sample standard deviation over the square root of n. In other words, the standard error of our sampling distribution. Okay, so let's go get those numbers here real quick. So the mu of the null was equal to 130. The x bar was given to be what? Well, our x bar was 134 calories. Our sample standard deviation was given to be 17, and our sample size was equal to 35. So that means that our test statistic z is going to be equal to 134 minus 130 divided by 17 over the square root of 35. Okay, so let's go ahead and do that calculation. So let's get our calculator up here to do that. So we'll grab the cursor here. Cursor is selected. Here's our calculator is selected. So seem to have a wee bit of stuff on my calculator, so let's go ahead and erase all of that, get that out of our way there. We don't want that there. There we go. Okay, so clear all this craziness out from algebra in there, and let's go ahead and do some stats. So be sure and open a set of parentheses for your numerator before you do this calculation. That big fraction bar is an inferred set of parentheses. You have to be explicit about that when you put it in the calculator. So there's our 134 minus 130, and then divide, and then we'll open a set of parentheses for the denominator. There's our 17 divided by second squared to get the square root of 35. Close out or get out of that square root by hitting the right arrow if you have a newer calculator. If you're on an older calculator, you have to close it off with a parenthesis and then put a second parenthesis to close off the denominator. So when you do that, you should get back 1.392. We'll go out 3 places here. So our z is going to be equal to 1.392. All right, great. So now that we know what our test statistic, our z is, we can use that to go ahead and calculate our corresponding p-value. So as before, whenever we're going to do any sort of a normal calculation, we're going to want to draw ourselves a picture that goes with it, okay? So come down here, make this our third step, calculate the p-value. And we're going to calculate this p-value in the distribution, the standard normal distribution, or the z distribution. So the corresponding p-value here is going to start with 0 at the origin. We're going to go out 1.392 to the left and 1.392 to the right. Okay, so that's about 1.392 this way. And then over here, we're going to be at negative 1.392 because this is a two-tailed test, and whenever you're doing a two-tailed test, that means I need to calculate the area in both of these tails to figure out what the total p-value is. So in other words, these two red shaded regions here are going to give me my corresponding p-value. All right, so how do we do that? Well, we can just calculate this lower one down here, and then we'll double that, and if we double that, that will give us the corresponding p-value. So the p-value is going to be equal to twice. Let's see, what's the lower end point? Oh, our left end point is going to be negative infinity, or in the calculator parlance, it's going to be negative E99, right? So it's going to be 2 times n for normal CDF. Left end point will be negative E99. Right end point will be negative 1.392. Mean is going to be 0. Standard deviation is going to be 1. Okay, so let's go ahead and do that calculation. It's going to go 2, and then we'll go second distributions, normal CDF, which is option number 2. We'll put in negative 1 second E99. That's my lower bound. My upper bound is negative 1.392. The mean is 0, standard deviation is 1, paste the command. Okay, so now if you had to type that in by hand, that's what it's going to look like. Don't forget your commas in between them if you're not on one of the newer fancy schmancy calculators, okay? So we hit an enter, and we get back our corresponding p-value, which is 0.164. We'll round off to 3 places, okay? So the p-value here, let's get that calculator back because I need that number. My pen's back here. So the p-value is going to be equal to 0.164 if we go out 3 places there, okay? All right, so the gold standard in calculating a hypothesis test, actually I'm going to go ahead and get rid of the calculator now because I need the whiteboard here. The gold standard is the 5% amount, okay? So it's time to make a decision here. So our 4th step is to make a decision. So what is our decision going to be? Well, we see here that the p-value is greater than 0.05, which we talked about that in the reading, why that's the gold standard, the 5%. So what that tells us is that we fail to reject the null hypotheses. There is not sufficient evidence to reject the hypothesis that the mean value is equal to 130 calories, okay? So the data doesn't provide convincing evidence that the true average calorie content in the bag of potato chips is different than 130 calories, okay? Hopefully that all makes sense. If you need any additional help with this, do not be shy about posting a question to the Q&A forum.